All right, in the last video, we looked at finding critical points. In this one, we're going to look at how do we classify critical points as being either a max, min, or neither. And how can we do that algebraically? So what we want to do to open up this idea is think about a quadratic function of the form ax squared plus bxy plus cy squared. And we know that near most critical points, so near most local max and mins, a function is going to have the same behavior as its quadratic Taylor approximation about that point. In other words, local max and mins typically behave like quadratics. So if we can understand how quadratics behave, then we can understand how their Taylor approximations will behave, and then we can let all local max or mins, we can impose upon them a Taylor approximation and use that Taylor approximation, quadratic Taylor approximation, to find whether or not it's a max or min. So what we'll do, therefore, is start by investigating the critical points of quadratic functions of the following form. And then we're going to use our findings from that and expand upon that to think about the implications of that due to or from or using, rather, quadratic Taylor approximations. Okay, so let's say we have this function. And we want to find and analyze the local extrema of the function. Well, first of all, I know that my critical point is going to occur where my partial derivatives equals 0. So when this equals 0, you know that y equals negative 2x, and this one has to equal 0. So if we were to plug this value in for y, we know that x plus 2 times negative 2x must equal 0. Negative 3x equals 0. This will only occur when x equals 0, and therefore when y equals 0. But how do we determine whether it's a max, min, or neither? And that's what we're going to talk about right now. So let's think about how we can complete the square of a quadratic equation, a three-dimensional quadratic equation. So in general, any quadratic of this form has a critical point at 0, 0, provided that a doesn't equal 0. So what we can do is we can take our function and we can factor out an a. And that's what we did in this step. We factored out an a. And then we're going to look at just the first two terms, and we're going to complete the square. So what we're looking at is taking b over a times y and dividing it by 2 and then squaring that, because that's how you complete a perfect square. And what we get is b squared y squared over 4a squared. And that's so what we're going to do is we're going to add this here and subtract it as well. So we get a times x squared plus b over a xy plus b squared y squared over 4a squared minus b squared y squared over 4a squared plus c over a y squared. So notice all that I did is that I added something and then subtracted it right away. Other than that, I didn't change my equation one bit. Here I had the x squared. But what this allows me to do by writing it like this, by adding in the completing the perfect square component, is that I can write my first term as x plus d over 2a y squared. So I wrote this as a perfect square, this component. And then I'm going to factor out a y squared, and I get plus c over a, and that's coming from right here, minus b squared over 4a squared, factoring out a y squared. And now we have exactly this form here. And to get down to the next line, what we've done is we've just gotten a common denominator. And so we get this new form of my quadratic. And this form tells me a lot about the shape of the graph. So the shape of the graph depends on the coefficient of y squared. And the coefficient of y squared is exactly this term here. And if the coefficient of y squared is positive, negative, or 0, tells me about whether or not our function has a local max, min, or neither. Well, let's investigate a little bit further. We know that for a squared, because of the a squared, we know that this is always positive. So what will determine the sign of my y squared value, what determines that sign is the discriminant, this value up here. And we call that d. And that value d, the discriminant, will determine the sign of my coefficient of y squared. And what we know is that if d is greater than 0 and a is greater than 0, the function has a local minimum because the graph will be a right side up paraboloid. And if d is greater than 0 but a is less than 0, looking at this a term, then the function is going to have a local max because the graph will be an upside down paraboloid following something like this. If d is less than 0, it's going to be a saddle, so it's neither. And if d equals 0, then the quadratic is a parabolic cylinder. In other words, y is a non-factor. I don't know if that's not really correct to say it's a non-factor, I guess. Let's take that out. Parabolic cylinder being something that looks like that. So there would be my parabolic cylinder. And this has neither a max or a min. Well, I guess it always has a min at y equals 0. But there's not one specific local extreme point. Okay, so here we have a nice summary of those findings. So provided that our discriminant is greater than 0, a greater than 0, we've got a local min. Here we have a local max. If d is less than 0, it's neither. And if d equals 0, we're going to have a parabolic cylinder. So we could expand that. What we were looking at there is just, if we had the point when x equals 0, y equals 0, z equals something. But we don't need to focus solely on having a local max or min at the origin. It also could occur at some point x naught and y naught. And this is going to have the same shape of our graphs that we were looking at before, except that our critical points are no longer 0, 0. They've been shifted to x naught, comma, y naught. And we could develop an analogous method for determining, the discriminant value and the a value and whether or not it's local max or min. But we're gonna go to an easier method, which is to use quadratic Taylor approximations. We know that having done these quadratic Taylor polynomials before, we know that we can approximate f of xy as a quadratic Taylor polynomial around 0, 0 as the following. What we can then recognize is that this is falling into the same type of graph that we were looking at before, where we have, our x squared. Here's my x squared coefficient. Here's my xy coefficient. And here's my y squared coefficient. So therefore, my discriminant, which is 4ac minus b squared, I've got my 4, my a coefficient, times my c coefficient, minus b squared. Here's b squared. And that simplifies to just f double partial in the x direction, f double partial in the y direction, minus f partial xy squared. And this is my discriminant. What am I going to do with that discriminant? Well, I'm going to look to see whether it's positive or negative. And if it's positive, we're going to have a local max or min. If it's negative, we're going to have a saddle point. And if it's 0, we're going to have a parabolic cylinder. So, if d is greater than 0, and my a term, which is f partial xx, is greater than 0, then we have a local min. And if d is greater than 0 and f partial xx is less than 0, local max. If d is less than 0, then it's a saddle point. And if d equals 0, well, the fact is, for this specific case, if d equals 0, we're not sure what's going on. Anything can happen. So then we have to do some more tests. But the key thing is that we don't need a quadratic equation now. Our function can be anything. It can be any sort of function. All we need to do is look at the second order derivatives, and from the second order derivatives, we're going to use that to approximate a quadratic Taylor, and from that approximation, we can determine whether we're having local max or local mins. So let's look at an example of that. Why don't we? It says find the local max, min, and saddle points of this function. So first thing we need to do is find the partial derivatives. So we have 2x minus 3y minus 9, and f partial y is 9y squared minus 18y minus 3x plus 9. For these to be true, or sorry, for us to have a local max or min, my partial derivatives need to equal 0. Or in other words, looking at the top one, x must equal 4.5 minus 1.5 y. I realize I just made a mistake there. This shouldn't have been a 2 here. which is going to change this a little bit. That derivative came from here. That should just be x. So therefore, yeah, this cleans up nicer. We have x must equal 9 plus 3y, and that would make my partial with respect to x 0. And then we can plug this in for here. So we're going to get the equation 9y squared minus 18y minus 27 minus 9y. That's plugging that value in for x, plus 9 must equal 0. Simplifying this a little bit, we have 9y squared minus 3y minus 2 equals 0. All right. Sorry, I made another slight mistake. That's okay. Hopefully you caught it. This should have been here plus 18y. That's plus 18y. And this will work out a lot nicer. Then we get 9y, pulling out a 9, we get y squared plus y minus 2 equals 0. Factoring that, this is going to be true when y equals negative 2 or 1. And when y equals negative 2, x equals 3. And when y equals 1, x is going to equal 12. And that's just plugging the y values into there. Now let's do the actual determining whether or not these are local max or mins on the next page. Okay, so now we need to find the second derivatives here. So we have f partial x double partial x, f double partial x is just 1, taking the derivative of that with respect to x, and f partial x y is negative 3, and we know that f partial y is going to be 18y plus 18, and then that all goes away. Okay, so let's look at each point one at a time. So we have the point 3, negative 2, and this, no matter what, is going to be 1, and no matter what, f partial x y is going to be negative 3. And then the last one, when I plug in negative 2 for y, I get negative 18. So using this equation, I get that my d value equals 1 times negative 18 minus negative 3 squared. And this value is less than 0. Therefore, we know that it is a saddle point. But what about the other point, the point, let's see, the point 12 comma 1. So I know that these values don't change here. The only value that's going to change is f partial y, which is going to equal, if I plug in the point 12 comma 1, we're just plugging in 1 in for y, that's going to equal 36. So for this value, we get d equals 1 times 36 minus 3 squared, which is greater than 0. And we know that f partial x is greater than 0. Therefore, what do we have? Well, here's our solution here, but we don't need this solution. We know that we must have a local minimum because our d value is greater than 0, our f partial x is greater than 0, so therefore this is a minimum at that point. That point is a minimum, and this point was a saddle. Takes a little bit of work, but it's a tried and true method where we can identify critical points and then whether or not they're maxes or mins. Okay, so let's do another example. Let's just look at this value right here. We know that fx equals 4x cubed. That's going to equal 0 when x equals 0. And f partial y equals 4y cubed, which will equal 0 when y equals 0. And we know that f partial x is 12x squared. F partial x partial y is 0. And f partial y equals 12y squared. And this equals 0 when x equals, oh, sorry, just leave it like that. So at our points of interest, we know that this equals 0. This is always 0. And f partial y equals 0. What this illustrates here is that d equals, well, 0 times 0 minus 0 squared, which is 0. This is one of those places where we can't determine it. And if we went and found d for this function and for this function, both of those d values are also 0. So there are times when we get to this place and we evaluate it and we get to d equals 0 and it doesn't tell us anything. But what you can do is you can know what a function looks like. You can know that this function is opening up, that it looks something like this. Whereas this function is going downwards. And this function here is a saddle. So here we're having a max. And over here we had a min. Even though our d value was 0. All right, well, let's do one or two more examples. In this, we want to determine, first find the critical points and then determine whether they are local max or mins. So first thing, always find the partial derivative. We have 2x minus 2. And f partial y is 2y minus 4. So we get when x equals 1 or y equals 2. Now, hopefully this looks somewhat familiar to you because this is the problem that we opened up with. So we know that we have a critical point at the point 1 comma 2, and we need to determine whether or not that is a max or a min. So now let's find the second order differentials. So we have 2 for that, 0, and 2. So my d value is 2 times 2 minus 0 squared, which is greater than 0, and f partial x is greater than 0. Therefore, we know that we have a minimum. And we showed this earlier using a different method, but here we're using our second derivative test for functions to determine that it is in fact a minimum. And it all requires that we take our function and we do a quadratic Taylor approximation on it, and using our second order differentials to determine when a function has a max or min. All right, let's do our very last example here. We're going to determine the critical points and then whether or not they are maxes, mins, saddles, or we can't tell. So same as before, find the partial derivatives. So we do that. Here, and partial with respect to y is 2x minus 10y plus 48. We want to know when these equal 0. So if I look at my top equation, I know that when 2y equals 6x plus 4, or when y equals 3x plus 2, that f partial x will equal 0. And then I can plug this value in for y here. So when 2x minus the following equals 0, then f partial y will be 0. So let's see when this is. So 2x minus 30x so when negative 28x equals negative 28, or when x equals 1, and when x equals 1, y equals 5. So that will be my critical point, and then to determine whether that critical point is a local max, min, or neither, or a saddle point. Let's look at our second derivatives. So here we have negative 6 and negative 10, and f partial xy is 2. Independent of the point. Independent of the point. Notice that the variables go away. So my d value is fxx times fyy minus 2 squared, and this is greater than 0. And we know that f partial x is less than 0. Therefore, my point 1 comma 5 is a local max.